We talked about unsteady state heat transfer, where we don't have the lump capacitance assumption. In other words, we assumed the bio number is very large so that the temperature deviation in the solid is significant, cannot be taken negligible. So we work with large bio numbers. Again, that was an assumption. You can also say maybe the bio number is like moderate and you want to just get a more general picture of what is going on. In other words, you don't want to neglect either the surface resistance or the internal resistances to heat transfer. So you say that the resistance to heat transfer within the solid is pretty much comparable with the heat transfer resistance at the surface, the convective heat transfer resistance. In other words, you can say, let me take my bio number close to 1. So today we're going to talk about the third situation. The first day we talked about this case. Bio number is much, much smaller than 1. When we say much, much smaller than 1, we mean like generally smaller than 0.1. When it's smaller than 0.1, then you can make the assumption that bio number is much, much smaller than 1. Okay, that's just the rule of thumb. And yesterday, we talked about another situation where you have a smaller resistance here, but a larger resistance here. Suppose bio number is much, much larger than 1. Now today, let's talk about the following situation, where you have either resistances are pretty much comparable to each other. Okay, bio number is in the order of, or approximately equal to 1. Okay, let us focus on bio number is almost equal to 1, since we have covered the other two cases. Now, this time the problem is going to be a little more difficult. So let me also briefly say that the bio number almost equal to 1 means surface and internal resistances are both finite, and none of them is negligible. Okay. Can somebody tell me for these cases which one is negligible, which one is not? When bio number is much, much larger than 1, what do we mean? Which resistance is negligible? The surface or internal? What do you think? Any idea? Am I experiencing a larger resistance to heat transfer within the solid or outside the solid? So as you can see, the heat transfer, the resistance to heat transfer is much, much larger within the solid because of the profile. You have a larger temperature difference, right? It doesn't allow the temperature to conduct, or the heat to conduct within the solid really well. So it's not like good homogeneity, right? But on the surface, you have negligible convective heat transfer resistance. So negligible surface resistance. Okay, is that clear? And for the black one, it's the negligible internal resistance. So think about the metal case, for example, metal versus plastic. So the metal corresponds to generally the black one, the plastic corresponds to the red curve. So for metals, in comparison to plastics, you have a better conductivity, so you have negligible internal resistance to heat transfer. So the metals don't resist at all to heat transfer. So you can transfer the heat much easier within this within the metals, for example, as opposed to plastic material. Okay, so that's an example. But this time we're going to talk about the Biot number, which is close to 1. So something between 0.1 and 10 would actually be in this range. Let's write it down here. 0.1. Or let's say this. When we say Biot number is approximately 1, we mean (0.1) and 10. The Biot number is between 0.1 and 10. Okay, so that means it's practically in the same order of magnitude with 1. So we think about the order of magnitudes. And let's go with the slab geometry. Let us work with slab geometry again to make things simpler. And let's have TF, fluid, with a temperature TF, heat transfer coefficient H on both sides. And you have X is equal to 0, X is equal to L. And the shell balance, you do the shell balance, right? Results in the same governing partial differential equations. So we do not need to redo them. No need to redo. We don't need to reinvent the wheel. But so if my shell balance is going to give me the same partial differential equations, am I going to get the same solution? What do you think?
No.
No, why not?
Maybe the boundary conditions and the initial conditions are different.
Exactly. So the boundary conditions and initial conditions will be different. For this case, it's the boundary conditions. Conditions are different. And when you have the same differential equation but different boundary conditions, you definitely have completely different solutions. That's the actual difficulty in partial differential equations and ordinary differential equations. So the problem with the differential equations is you should never say that, oh, I know how to solve for example, this partial differential equation, you never know before you know the boundary conditions. Your solution is going to be completely different with different boundary conditions. Okay, that's one of the take-home messages you should learn in transport process class. Sorry, I dropped my pencil. Let me check it. Okay, good. So I have the same del theta over del psi squared is equal to del theta over del t tilde. But I should define what I mean by theta and t tilde and psi, because this is a different problem. Theta, let's define it as not T minus T surface, but T minus TF, because now my characteristic temperature is the fluid temperature, not the surface temperature. Divided by.
Professor, wasn't it del squared theta?
Yep, del squared theta, exactly. Thank you for the correction. T0 minus TF. And my psi is the same as in the previous problem, x over L. Okay, and the time, T tilde, is T over characteristic time, and the characteristic time is L squared over alpha. Okay, those are all the same. The only change is the theta is defined with respect to the fluid temperature, which is our only, which is our one of the characteristic temperatures. Okay. Okay, but we get the same, like a similar situation. We're gonna have like theta is equal to, our solution is gonna look like C1 sine lambda n psi plus C2 cosine lambda n psi exponential minus lambda n squared t tilde, right? And if you remember, this is my like f psi gt gt tilde without the boundary conditions implemented. Now I'm going to implement the boundary conditions. Okay. For this one, I have a difficult boundary condition at the at the surface here. I'm going to think about the fluxes using the Newton's law of cooling. I can do it twice. I can say at x is equal to 0, I have that. At x is equal to L, I have that. Like convective heat transfer is equal to the Newton's law of cooling. But let me just make it simpler by using another boundary condition at the center here. Okay. And we'll see that this is the symmetry axis, right? We're going to use symmetric boundary condition, or I would say symmetry boundary condition. Let's call it boundary condition 1. And it says that at midpoint at psi is equal to 1/2, del theta over del psi, which is equal to some multiple times the del t over del x, right? But del t over del x is going to be 0 just because of the symmetry. Okay, so my profile is symmetric. I claim that my profile is symmetric at all times. Like, imagine something like this, right? Since you have the same TF on the left and right, your problem is a symmetric problem, and you would be so surprised if you get a temperature profile like this. If your initial temperature profile is this, I mean, it would be symmetric on both sides, and I would be really surprised if I get something like this. So it's never going to happen. So your temperature profile must be symmetric. So that's why the derivative of the temperature at the center must be 0. That's what we call as the symmetry boundary condition. Whenever you have a symmetric problem, you can actually assume that. And let's find the derivative of the theta using this. Right? And you get the sum over n, right? So, the derivative of sine lambda n psi is lambda n cosine lambda n psi. So that's C1 lambda n cosine lambda n psi. But instead of psi, I'm going to plug in 1/2. Okay. Plus C2 lambda n. That's going to be minus sine, right? Lambda n 1/2. Okay. Times exponential minus lambda n squared t tilde. I don't know whether the lambda n's are like n pi's or so, because I have different boundary conditions. Maybe I'm going to get different lambda n's, right? So let's solve this. From here, you should say that this is equal to 0 for any t tilde, right? For any t tilde. But I can make this any number. So that means this must be 0 for each and every n, because if I had non-zero values, I would be able to make this entire thing non-zero by playing with the this number exponential, correct? So that means this must be 0. 0 for all n. Okay. That means 0 is equal to C1 lambda n cosine lambda n over 2 minus C2 lambda n sine lambda n over 2. And let's get rid of the lambda n's. And you get C1 over C2 is equal to tangent lambda n over 2. Right? That's one of the results of the first boundary conditions. Okay, then we should plug in this result. So the theta looks like the following: sum over n. Instead of C1 and C2s, let me take into the C2 common parenthesis. C2. The first term is going to be C1 over C2, right? But instead of C1 over C2, I'm going to write down this tangent lambda n over 2, which is a constant which depends on n, sine lambda n psi, plus there were C1, C2 here, but I took it out of the parenthesis. So I have cosine lambda n psi exponential minus lambda n squared t tilde. Okay. One could argue that like you had bn's here, right? But you can think of it as if like it's like it's absorbed in like C1 and C2. So we should be good in that sense. But we should actually keep in mind that it might depend on n. Okay. Good. So the boundary condition 2 is, now I must actually use a boundary condition at the surface, maybe for at psi is equal to 0, right? At psi is equal to 0, the flux Q at x is equal to 0 must be equal to minus k del t over del x at x is equal to 0 within the solid must be equal to the Newton's law of cooling, the H times Tf minus T at x is equal to 0. Now, this thing is going to be positive if the flux is to the right. And if the flux is to the right, I need to make this one positive as well. So Tf is going to be larger than T because the heat is transferred from left to right, right? So you get a positive value on both sides. So that makes sense. If on the other hand, this thing is to the left, or in other words, this thing is negative, I must make this negative as well. So if this is negative, that means Tf is smaller than T. This would be negative, so that's okay. So I don't need to put any extra sign in front. So that makes sense. You can check it only for one case where one of them is hotter than the other. Good. And you need to write the T's in terms of thetas. So instead of Tf minus T, you can write minus theta times T0 minus Tf using the definition of theta here. Using this, you can solve for T minus Tf and then Tf minus T, and then it's theta times T0 minus Tf, but it's the other way around, so it's minus of that. Okay. And similarly, for this one, this is basically del theta over del psi. That's yeah, T0 minus Tf divided by L, right? This entire thing is. So after the simplifications, after you actually get rid of these, you find that K over L del theta over del psi at psi is equal to 0 is equal to theta, h theta. Yep. At psi is equal to 0. So from here, del theta over del psi at psi is equal to 0 must be equated to HL over K theta. So now this is my boundary condition, and I'm going to apply it to the expression for the theta here. Okay. And the left-hand side is the derivative with respect to psi. So you get sum over n C2 tangent lambda n over 2. I don't take the derivative of that because it's a constant. It's not a function of psi. But the sine lambda n psi is a function of psi. And it's basically lambda n. The derivative is lambda n cosine lambda n psi. But the psi must be 0, right? So this thing is 1. plus lambda n. Well, actually, it's minus lambda n because the derivative of cosine is minus sine. Sine lambda n psi. Again, the cosine should be set at 0. Exponential minus lambda n squared t tilde. And this is 0. Any questions so far? That's your left-hand side. And the right-hand side is, I mean, we did this part, now we're going to do this part. H L over K. Theta at psi 0 is sum over n. C2. I'm not going to write down the sine term because it's going to be 0. It's just cosine lambda n psi. Psi is 0, so cosine lambda n psi is 1. So let me just write 1 there. Then exponential minus lambda n square t tilde. So I get sum over n, C2, tangent lambda n over 2, lambda n, right, is equal to HL over K, sum over n, C2, exponential minus lambda n t tilde. But I want this equation to be valid for all t tilde, right? I'm actually missing one term on the left. I'm sorry. Let's select this, take it to the right. Okay, and place this exponential minus lambda n square t tilde term. There you go. Now I want this to be valid for all t tilde. So the this term must be equal to this term for any n. Or in other words, you can subtract right from the left to get the sum over n. C2 lambda n tangent lambda n over 2 minus HL over K exponential minus lambda n t tilde. So I want this entire thing to be 0. So for any t tilde, that means this must be actually 0, because otherwise it's not actually possible to make this 0 for all t tilde. Otherwise it's going to change with the t tilde. I don't want it to change with t tilde. So for all n, this term must vanish. So you get basically C2 cannot be 0 because it would be trivial otherwise. So lambda n, I mean this term must be 0. So lambda n tangent lambda n over 2 must be equal to HL over K. Okay. Let's write the right-hand side in terms of the Biot number. What's the Biot number for this system? We define the Biot number as h times length characteristic divided by k, and the length characteristic can be found by dividing the area to the volume of the solid, right? And then this is a more general definition than using any L length. And you have h, the volume is the area of the slab times the thickness, right? L. let's say this is the total surface area. The cross-sectional surface area times the L divided by the total area of the slab. The total surface area is 2 times the cross-sectional area, because you have 2 sides. Okay, it's in contact with fluid on both sides, so you add them, divided by K. So you get, for this slab geometry, H L over 2 over K. That's your Biot number. So in other words, your right-hand side is basically 2 times the Biot number of your system for the slab. 2 times Biot number. And you can have lambda n over 2 tangent lambda n over 2 is equal to Biot number. Then you basically solve the following equation. Tangent lambda n over 2 is equal to Biot number over lambda n over 2. Okay. In other words, you should solve the following equation. Or you can actually play with this, and you can say lambda n over 2 divided by Biot is equal to cotangent lambda n over 2. And you would say, I need to find out the solution to the following equation. X over Biot is equal to cotangent x. Okay. And if you find the solutions, then you can actually find the lambda n's. And here's how you can find it graphically. The cotangent x looks like following. If this is pi, 2 pi minus pi minus 2 pi, and yeah, let's do these. If you remember from your trigonometry classes or calculus classes, the cotangent function should look like this. Right? It's going to be periodic. And that's your cotangent x. And let's also draw x over Biot is a linear function, right, as you know. So at x is equal to 0, you get 0, right? And then it's going to have a positive slope. Let's call this x over Biot. So the intersections, oops, let me delete this. Anyway. The intersections correspond to the solutions of the above equation, right? And this corresponds to, for example, okay. So each of them is basically some lambda n. Okay, so you can think of it as like lambda 1, lambda 2, and so on. Okay. And like graphically, you can actually get these numbers, or using like computer, some code, you can find out the lambda 1, lambda 2, lambda 3, etc. well, to be more precise, this corresponds to lambda 1 over 2, lambda 2 over 2, because basically we referred x to be lambda n over 2, right? Okay, so these are going to give you the lambda n over 2 values. So let's write it down. Solution to lambda n over 2 are given by the points of intersection between the function y is equal to cotangent x and y is equal to x over bio number. So the solution to lambda n over 2 are given by the x-axis, or the x component of the points of intersection. Okay, good. There you go. So basically, you can write your solution in series sum, right? Theta is equal to sum over n, the C2 tangent lambda n over 2 sine lambda n psi plus cosine lambda n psi exponential minus lambda n squared t tilde. As I said before, the C2 might depend on n, right? And you need to find it. And instead of C2, you can just call it like as we did before, Bn, right? And then it's going to be constant depending on n. You can use the orthogonality relations. Now, you can use first boundary condition, initial boundary condition. You can use initial boundary condition or the initial condition to solve for Bn's, but you need the orthogonality relations as well. Okay, so I'm not gonna go into that. Just I leave it to you as an exercise. Okay, so this is all about how you can tackle with the problem when the bio number is comparable with 1. Okay, when you have significant surface and internal resistances.